All right, let's get right into it. Today, we're going to peel back the layers of your computer and look at the absolute foundation of how it thinks, the simple, tiny circuits that let it do math. I mean, it's a question we rarely think about, right? You punch numbers into a calculator or a spreadsheet, and the answer just appears. But it's not magic. It's the result of millions of tiny, unbelievably fast calculations happening on a microscopic level. So, how does a machine that only understands on and off actually add two numbers together? Well, the answer lies in this little hero, the adder. An adder is a special kind of digital circuit, and its one and only job is to perform addition using binary code. Yep, the language of ones and zeros. This thing is the fundamental building block for all arithmetic inside your processor. Now, it's not just one size fits all. We're going to meet the two main players in our story today, the simple but kind of limited half adder, and its more powerful, more versatile big brother, the full adder. So let's start at the very beginning. Before you can tackle complex calculations, you've got to master the basics. And in the world of digital logic, that basic first step is the half adder. The job of a half adder is, well, beautifully simple. It takes in just two inputs, two single bits, we'll call them A and B, and it gives you two outputs, the sum, which is the result, and a carry, which you might remember from elementary school math class. And here's how it works, all laid out in what's called a truth table. Now, the first few rows are easy. 0 plus 0 is 0. 1 plus 0 is 1. No big deal. But look at that last row. 1 plus 1. In binary, the answer is 1, 0, which is just how we represent the number 2. So the sum output is 0, and we generate a carry of 1. This idea of carrying over, it's absolutely crucial for everything that comes next. So how does the circuit actually pull this off? It's not magic. It's just logic gates. This sum is calculated using an XOR gate. You can think of that as the one or the other, but not both gate. It only puts out a 1 if its two inputs are different. The carry, on the other hand, is calculated with a simple AND gate, which only gives you a 1 if both inputs are 1. That's it. It's really that simple. So you can kind of picture it, right? Two bits, A and B, flow into the circuit. They basically hit two gates at the exact same time. The XOR gate figures out the sum part of our result, and the AND gate figures out the carry part. Two simple operations, one simple result. So this seems perfect for adding two single bits, but what happens when you want to add bigger numbers? Numbers with multiple digits. That's where our simple half adder runs into a very, very big problem. Think back to doing long addition in school. When a column added up to 10 or more, what did you do? You wrote down the last digit and you carried the 1 over to the next column to the left. Well, binary math works the exact same way. You've got to have a way to handle a carry that's coming in from the previous addition. And here it is, the fatal flaw. If you look at the half adder's design, it only has two inputs, A and B. There's just no third input for that carry in bit. And that means it can only ever add the very first column of bits in a number. For anything more complex, it's basically a dead end. So how do computers solve this problem? Well, this is where the hero of our story steps in, the full adder. It's a circuit that was specifically designed to overcome this exact limitation and make all kinds of complex math possible. The genius of the full adder is right there in its definition. It doesn't just add two bits, A and B. It adds three bits, A, B, and a crucial third input called sin, which stands for carry-in. This is the missing piece of our puzzle. Let's just look at a couple key lines from its truth table. Check out that last row. What if you have a 1 plus another 1 plus a carry-in of 1? What do you get? Well, in binary, that's 1, 1, which is how we write 3. So the sum is 1 and the carry-out is also 1. The full adder can handle every single possible combination you throw at it. And here's the truly elegant part. You don't have to throw away our old half adder. In fact, our flawed little component is the main building block for its own, more powerful successor. And this just brilliantly shows a core idea in digital design, building complex systems out of simpler parts. So here's how it's done. The first half adder adds A and B. The sum that comes out of it gets fed into a second half adder along with the carry-in bit. The final sum we need comes from this second adder. Then, to get the final carry out, we just use an OR gate, which, remember, outputs a 1 if either of its inputs is 1, to combine the carry signals from both of the half adders. It's an incredibly clever and efficient design. Okay, so we've got these two components, the half adder and the full adder, but how do they go from being these abstract diagrams to actually powering the world around us? Let's connect these simple gates to their massive real-world impact. So let's just quickly recap the key differences. A half adder, two inputs, no way to handle a carry-in, it's super simple, and it's really just for single bit addition. The full adder, three inputs, it does accept a carry-in, it's a bit more complex, and it is the absolute key to adding numbers with multiple bits. That carry-in capability, it's everything. See, because full adders can be chained together, with the carry-out of one becoming the carry-in of the next, they form the very heart of the arithmetic logic unit, or ALU, that's inside every single microprocessor. They are the reason your computer, your phone, and pretty much countless other digital systems can do math at all. And what about our simple half adder? Well, while it's not the star of the show, it's still crucial. Its main role these days is for educational purposes, to teach the fundamentals, and most importantly, to act as that essential building block inside every single full adder. So if you remember anything from all this, remember these three things. A half adder is just one XOR gate and one AND gate. A full adder is cleverly built from two half adders and an OR gate. And the superpower of the full adder, the thing that makes all of modern computing possible, is its ability to handle that carry-in bit. And that kind of leaves us with a final thought. We've seen how something as fundamental as addition can be built from these incredibly simple logic gates, just combining simple parts to create something way more powerful. It really makes you wonder, what other complex ideas, from graphics to language, maybe even to artificial intelligence, are ultimately just clever combinations of these simple ones and zeros?